fellow physicists, and welcome to another episode of Curious Conversations. Today I'm joined by an astrophysicist whose 2009 Ph.D. thesis titled Ultra-High Energy Particle Detection with the Lunar Cherenkov Technique was recognized by the Australian Institute of Physics with the Bragg Gold Medal, which is awarded for the most outstanding Ph.D. thesis in the country each year. Following this achievement, he took postdoctoral positions in the Netherlands and Germany before returning to Australia to work at the International Centre for Radio Astronomy Research, specializing in the fields of astroparticle physics and fast radio bursts. He also lectures in nuclear and particle physics and electromagnetism at Curtin University. Dr. Clancy James, welcome to the show.
Thank you very much. You can't see me blushing behind this mask at the moment.
So in that little introduction there, I mentioned cosmic rays. That's obviously one of your big research topics. So what are cosmic rays?
Well, one of the first things I want to point out now is it's a little bit disappointing because we do know what cosmic rays are now. But if you want to do an interesting Google search about the interaction between science and the media, back in around the late 20s, early 30s, when cosmic rays, were an intense subject, there was a big debate between two Nobel Prize winners about what cosmic rays actually were, Compton and Millikan. And this got a little bit heated at times. We now know cosmic rays are basically atomic nuclei. Right, when people talk about cosmic rays, they're usually referring to the 90-something% protons, then helium, etc. The same elements that just make up our galaxy, right? Same stuff that makes up stars. It's just that they've been accelerated to a very high energy. So if any of the listeners are familiar, or at least aware of the Large Hadron Collider and particle accelerators, either through science or through popular culture, right, these devices take particles and accelerate them to almost the speed of light, not exactly, but very close, and give them a lot of energy in the process. And cosmic rays are exactly the same way. It's just that it's some physical phenomena in the universe that's accelerated these things other than a man-made apparatus. I guess the other specific to note regarding cosmic rays is that we do get high-energy charged particles from the sun, and they can be relativistic. But cosmic rays are sort of now, by definition, usually the component that's from outside the solar system. Now, some will come from our galaxy, some from outside the galaxy, but we don't know exactly where, and that's, part of the research. And I guess one of the first things that you should know about the cosmic rays and why they're interesting is that I mentioned they can get up to highly relativistic energies, right? The highest energy cosmic ray ever observed had an energy of about 50 joules in a single particle, right? So this is the equivalent of dropping a brick from about a meter, right? That much energy in a single atomic nucleus. So this is about 10 to the 7 times as much energy in a single particle as the Large Hadron Collider can produce. And something in our universe is accelerating particles to these extreme energies, right? And we don't know what.
And in your research in cosmic rays, there's been some association with neutrinos and gamma ray bursts. So how are cosmic rays related to those things?
All right, so the short answer would be come take nuclear and particle physics in third year and you'll find about the fundamentals. So there's two ways of answering this. One is the general, more hand-wavy answer, which is that they all get produced by, what we think, by high-energy phenomena in the universe. Right? As you mentioned, gamma ray bursts. So gamma ray bursts come in two classes. They're the short gamma ray bursts, which are mostly, say, neutron-star binary mergers and other binaries, and also the long gamma ray bursts, which are the collapse of supermassive magnetized rotating stars. And other phenomena are, normal supernova, right, which are still incredibly explosive events, but not up there with gamma ray bursts. Massive shocks from active galactic nuclei, so supermassive black holes from the centers of galaxies, shooting out jets of particles into intergalactic space, and these jets can reach up to, 1 million light years or more in distance. And these are the kind of phenomena that tend to accelerate particles to high energies. Now, when you accelerate a particle to high energy, it will sometimes radiate and produce high energy gamma rays, right? And so there are theories that some of the gamma rays from a gamma ray burst might be due to cosmic rays. The other thing is that when cosmic rays interact, they produce a range of subatomic particles in their collisions in exactly the same way in the Large Hadron Collider. When they collide protons together, they produce a range of particles. And neutrinos are one of these particles. One of the reasons why neutrinos are so important in this picture is that most of the radiation we see in the universe is due to electrons doing things. However, it's extremely difficult to get electrons to produce neutrinos. Technically, it's possible. It happens in the centers of supermassive stars at a very small rate, but it's very difficult. Whereas they're produced all the time whenever protons interact. They'll produce things called pions, which are subatomic particles that then decay to produce neutrinos. At a fundamental level, which you might understand at the last lectures of our electromagnetism second year subject, is that when you have a charge that's accelerating, that's what produces radiation, except in Cherenkov radiation, which we might get to later. So the idea is that neutrinos are kind of like the ultimate signature of high energy particle acceleration and point back to the source of cosmic rays. Yet when you see gamma rays, you're left with this quandary, right? What actually produced them? Then again, gamma rays are a heck of a lot easier to observe than neutrinos.
So you've explained what these things are, but why are they useful? What problems are being solved?
So let me first tell you the problem that isn't being solved, and that is what produces the highest energy cosmic rays. Right? This whole business began, I guess you could say, back in around 1908, if I remember my dates correctly. Please correct that in the video post-production, when a guy called Hess in Germany went up in a balloon and worked out that there was some radiation coming from space, right? Saw that there was more ionizing radiation at higher altitudes than lower altitudes. Since then, all of this has been motivated by the sorts of what in the universe is producing these high energy particles. We've got various ideas, and we think supernova and their remnants are responsible for medium energy cosmic rays. You know, cosmic rays that are merely at the same energy as the Large Hadron Collider, right? Which is still pretty high. But we still don't know what the source of the highest energy cosmic rays are. So that's a problem that isn't being solved, right? And we're still looking for that, and it's really darn difficult. Regarding what problems are being solved, so in general, the kind of environments where you expect high energy particle acceleration are shocks, right? So a shock is fundamentally when something is traveling faster than the speed of sound, right? Because if it's traveling at the speed of sound, the pressure can make things move smoothly, right? Whereas as soon as something moves faster than the speed of sound, whether or not it's the speed of sound in water or air for a sonic boom, right, or if it's faster than the speed of sound in an astrophysical gas, then things happen suddenly, right? And so wherever you get a shock, and that might be from the jets of an active galactic nucleus or the material shot off from a supernova explosion, then these are the kind of environments when we expect particle acceleration. So when people are using these experiments, they generally combine data from gamma ray telescopes. So there's a class of telescope called the Imaging Atmospheric Cherenkov Telescope, IACT, and they study high energy gamma rays, like around tera electron volt energies that might be emitted, perhaps, from cosmic ray interactions. One thing you might want to put up is an image of something called CTA, which is about to be the building of it's going to begin shortly, and Australia's part of that, even though Curtin isn't. And Hess is a current instrument of this kind, which is named after Victor Hess, who first discovered cosmic rays. Now, you combine information from the gamma ray telescopes, and you say, okay, this is where in the sky we see high energy gamma ray emission. You then take radio telescopes and X-ray telescopes, and you form what's known as a multi-wavelength picture of the source, because different energy photons probe different processes. Let's imagine we're looking at an active galactic nucleus, and there's something called a blazar. So this is the general way you draw something called a spectral energy distribution. So this kind of plot is called an SED. And here you have photon energy, this way. And so you might have gamma rays here, you might have UV here, X-rays sort of here, and radio, and optical, well, that's just near UV, infrared, etc. And this will be the energy, I didn't write the G well, energy in that wavelength, right? So lambda is the standard thing for wavelength. And so you make a plot of this, and for a blazar, this plot looks something like this, right, approximately. Yeah. This double hump. A blazar is where you have a supermassive black hole at the center of a galaxy. It's accreting a large amount of matter, and it's shooting out a jet. And the jet comes from within maybe 10 Einstein radii of the black hole itself. So it's not escaping the black hole itself, it's escaping from just before material falls in because there's a lot of pressure and it comes out perpendicular to the accretion disk. Now, this matter is primarily electrons and photons and maybe cosmic rays as well. Now, what you find is that the electrons are responsible for this emission here, right? So this left-hand bump, right? This is the low energy bump, and that's probed by radio, optical UV. You sometimes see a second little bump there, and that's due to UV radiation from the accretion disk itself, whereas this broader bump is due to the jet. Yep. Now, you use this to say, right, we've got magnetic fields in this jet coming out. There's electrons in there, they're being accelerated, and they're emitting synchrotron radiation, right? And we're 99 etc. sure that synchrotron radiation is what's responsible for this left-hand bump. Now, you then say, okay, if that's what's responsible for the left-hand bump, we have a lot of synchrotron radiation, and we have a good idea of what the energy of the electrons must be to produce it. So you've got a bunch of high-energy electrons flying around, a bunch of photons. They will sometimes interact with each other, and you get a high-energy electron, low-energy photon, and that will upscatter the high-energy photon to produce the second bump. So the standard explanation for this big bump here, right, this one there, is that these are photons that have been upscattered by electrons. So you have a high-energy electron that we don't directly observe, but we infer, causing radiation to go into the X-ray and gamma ray regime. So that's pretty much how people view blazars. Now, several years ago, the largest neutrino telescope in the world, called IceCube in Antarctica, observed a high-energy event, right? That's very unlikely to have come from the atmosphere. And that high-energy event it's a neutrino, and it had an energy around here, right? So the effective energy from that neutrino was a point there. Now, obviously, this is a plot that's usually done in photon energy, but you can clearly take the neutrino energy, just write this neutrino there, and you've got an equivalent flux around there. How can you produce a neutrino from this? Well, we don't know. When people tried to model this, you say, okay, well, what if there's cosmic rays in there? Well, let's put in some cosmic rays. And they said, well, we definitely can produce neutrinos from cosmic rays in here, right? But as soon as you get some cosmic rays in there, neutrinos aren't the only thing produced. They'll produce even more high-energy electrons. And it turns out that as soon as you put a flux of cosmic rays in there that's required to produce this neutrino, you actually expect an X-ray flux, like a flux in X-rays that looks a bit like this, right? And I guess I should have put X-ray there. There's different regimes of X-rays, obviously. It doesn't live in one spot. And so it was measured via X-ray telescopes and these are satellites, right? You can't do X-ray astronomy from the ground because we can all be thankful that X-rays don't make it through our atmosphere. We could show that our expected model of cosmic rays in this source was inconsistent with this multi-wavelength data. And yet we saw a neutrino coming from it, right? And it's extremely unlikely that this was a random coincidence. Not completely impossible, but maybe of order 1 in a million. So that's something that we're currently unsure about. We don't know how this object, called TXS 0506 plus 056, produced this neutrino. We're trying to find out. And to answer that question, we need information from radio, optical, UV, X-rays, gamma rays, neutrino telescopes, the whole shebang. Okay. So there's a particular example. I guess I could go into some galactic examples, but they have pretty pictures to do with them, but this is one source that's currently of most interest to me.
So how can undergraduate students contribute to astrophysics research like what you've mentioned?
Well, I guess I better have a good answer for this one, given that one of my current students, Anvil, is just sitting a few metres off screen. Yeah, so essentially, the ways you can contribute to the research is by taking an undergraduate project, either through one of the summer research projects or during the third year projects that are offered, and then, of course, go on through honours. Now, the way that we use these projects, it's both to get students to do some, generate some useful output. We do primarily, however, aim for it to be a teaching experience, right? So you might imagine that in a typical project, which if it's a summer research project, might be 6 weeks, and if it's an undergraduate project, let's say it's a nominal one semester project, that's really only one subject spread over 10 weeks, and so it's probably even less than that in effective time. So on the one hand, you might say sort of it's quite difficult to get students to make a useful contribution in that time, right? And you treat it as a learning experience, and then over the course of several projects, let's say someone does one summer project, then they spend an entire year at third year, and then that ramps someone up for honours. I guess our nominal working model is that honours level is a standard place where we expect people to be able to make a useful contribution, and the other projects might be chipping away at the edges somewhere, but it's primarily aimed at a learning experience of what research is like. Because, one of the things that I hope you sort of realise now is that research is nothing like lectures, right? Lecture, you're sitting there and being told facts. Research is when you don't know what the truth is, right? And how do you go from this sort of teaching mentality of school and undergraduate university where you sit back and some wise person tells you the truth and you just have to regurgitate it and learn how to solve problems in exams, to the point where nobody knows the truth. There's no one you can go to, and you have to be confident enough to understand that. So from the fundamental, solving these fundamental points, that's really what a research career is about. Having said that, there's a lot of aspects of these rather complicated experiments that undergraduate students can and have made useful contributions to. So, for instance, as a recent example, I've had a student work on one of the simulation programs that estimates the sensitivity of Antares, which is a neutrino telescope in the Mediterranean. That's a project I've worked with.
So not the star.
No, not the star. It is named after that, and the acronym is...
We can throw it on the screen.
Yeah, please find the acronym. I definitely can't remember it. And so this program, the idea simulates the process of a neutrino interacting in the water around the Antares experiment and detecting the light. Yet, so it implements a lot of pretty detailed physics to produce that. However, it doesn't implement precisely, and we were investigating how reliable this program is in terms of the contribution of something called a D meson. So these are very heavy mesons that then decay rapidly and can produce high energy muons that can then travel kilometres through water to be detected. And yes, please Google all that. And so this was the program that the student Mitch, who did that, worked on this for about a year. And as a result, we now know more about the effect of these mesons on our detection of neutrinos when we otherwise didn't, right? And that's simply because, these experiments as a whole are big, complicated things, and you need people to work on building apparatus, people analysing data, on simulating the experiment to understand how sensitive it is. So it's absolutely possible that even at a summer project or a third year level, you can contribute to genuine science that gets published in internationally peer-reviewed journals. Right? So I think that's, but don't expect that. The way to view this is to really get a taste of what research is for the first time, and then it would really be honours when you're starting to do what you would consider sort of cutting-edge science. And even then, what do you call cutting-edge science? Right? There's always different thresholds for this.
Well, that's all we've got time for this episode. So thank you, Clancy, for agreeing to be here today.
Thank you very much for giving this opportunity to talk for way longer than I probably should have.
If you want to see more content like this, make sure to hit the subscribe button and ring the little bell icon. Or if you want other people to see our videos, please like, share, and comment below.
And until next time, stay curious.